Okay, so let's kind of do a warm up of what we did last time, and then so we'll do a warm up of what we did last time, and then what we'll do is we'll kind of cover things slowly. And I don't plan on staying till 3:40 today. I plan on trying to stay till like 3:15 or something like that. Sound good?
Okay.
And I don't plan on trying to like blow your minds out with like everything under the sun. I plan on just kind of trying to take it easy and going through this stuff as we go. Because kind of continuing on my niceness to Bradley Bollinger, he sounds like he's had a pretty rough week. And so, Brad, this one's for you. I was going to say this bud's for you, but that's not appropriate. All right. Anyway. Yeah, because Bradley's going to explode. His head's not going to explode. I think he literally is going to explode. So we're going to cover stuff that is not so crazy for him. How's that?
Was it the homework on
No, actually, it wasn't my fault at all. Believe it or not. Well, at least I don't think so. The thing was my fault. It was,
I never said it was your fault.
Well,
I
no,
said it
I'm
was your
just-
fault. See,
All right.
because you said it was not your fault,
All
that
right,
means that it probably was your fault.
OH. This is potassium. OH is hydroxide, right? Yeah. OH. KOH plus, let's see. KOH plus ferrium nitrate. So it'd be, or iron nitrate, FeNO3. And there were, how many of the NO3s? There's 3 of them. Okay, so normally, if this is an aqueous solution, oh, oops, I didn't record this yet. Let's start up the recording. Did I? Oh, I did. I'm recording this. Awesome. All right. So normally, if we break this up into its ions, this KOH breaks down into K plus and OH negative, right? Those are the ions that it breaks down to. And then the Fe is, all right, the NO3, I know that one. I made you guys actually memorize that. That's just regular NO3 minus. That's normal charge on the NO3 nitrate. No, you memorized this when you guys made flashcards on the ions.
Oh, yeah. That's right.
This was back in quarter 1.
All
right, so if there's NO3 minus and I need 3 of them to balance out with Fe, what kind of iron am I dealing with? What kind of ion of iron am I dealing with? What's the charge on that one? If I need 3 negatives to balance it out, what's the charge on it?
Be positive.
3 positives. There we go, positive 3.
Okay.
So, and we need 3 of these. The 3 NO3s. Got it? All right. So now what we need to ask ourselves is, what, according to the rules, and we look back over here for the rules, let's see. If I'm going to add these 2 together, I'm wondering if this thing forms a type of compound. I'm wondering if not those 2. I'm wondering if these 2 form a type of compound. KNO3. And how many NO3s do I need? What's the charge on K?
Positive, right?
Positive. What's the charge on NO3?
Also, wait. Is it negative?
It's negative.
Negative.
So how many NO3s do I need?
Or 3 of them.
No, I need even amount.
So you
I just need 1 and 1. Yeah, okay. I don't need to put in any kind of number over here because this positive potassium gets balanced out with that -1 nitrate. Got it? All right. And then if I'm wondering if according to these rules, how many OH, by the way, do I need to balance out with the positive 3 iron? I'll need how many?
-3.
I'll need 3 OHs. Need 3 hydroxides. Got it?
Okay.
And then according to our rules, let's see if we can find some rules. Let's see. Most hydroxides are only slightly soluble. The more important soluble hydroxides are NaOH. All right, we don't have that. And KOH. Oh, okay. So what this is saying is KOH will dissolve in water. It's soluble. The compounds barium hydroxide, strontium hydroxide, and calcium hydroxide are marginally soluble. So this thing would definitely break down into its ions. And so because I know that, then I know that, let's see, FeOH. Do I see an FeOH? No. Iron hydroxide. Yeah, iron hydroxide is only slightly soluble, whereas KOH is an exception. It's soluble hydroxide. You guys see the rules that I'm quoting from the book here?
Mm-hmm.
And so based off of that rule, I can conclude that what's going to happen is your your equation is going to be KOH plus FeNO3 is going to yield FeOH 3 and plus KNO3. Now, this is going to be an aqueous solution. This is going to be an aqueous solution. You see that because in the problem they gave us that they were aqueous to begin with. See, aqueous and aqueous. Got it? And then the KNO3, that has to do with the nitrate rules, and is NO3 a soluble solution? The answer is yes. So I'm going to put an aqueous there. But then FeOH, that's a non-soluble solution. So that would create a what type of element, or what type of compound? A liquid, solid, gas, or solution, or aqueous solution.
It would be solid, right?
That would be a solid. That would be where your precipitate comes in. And that's that cloudy, murky stuff that's in the water. Masson, did you watch the video from Monday?
For Monday?
Yeah.
No.
Okay. Well, a lot of this stuff we covered on Monday. This problem, I think I did part A and B on Monday, but I didn't do part C, and this is part C.
I had a super busy Monday, Tuesday.
All right, so why did you combine Fe and OH? Well, it's because if I combined K and OH, then I would really just get the same thing back that I started with. You know what I mean?
Mm-hmm.
And if I combine the Fe and the NO3, then I would get that thing back that I started with. And I was thinking that there was a reaction that's going to happen. So I would need this ion to combine with this ion to make something different. What's wrong with getting the same thing back? There's nothing wrong with getting the same thing back. In fact, the first problem we did, we got the same thing back, and we concluded that there was no reaction that would take place. The thing that I love your questions because they're really asking deeper understanding things, but there is nothing wrong with getting the same thing back. The rules on whether or not you would get the same thing back or you would get something different back depends on these solubility rules. And there's just these list of 6 rules that we have. So apparently, KOH, which is right here, is soluble. It's a hydroxide that breaks the rule of only being slightly soluble. It's very soluble. So because it's very soluble, it will break down. Does that make sense? And it probably won't form KOH again because it likes to break down. It's a soluble solution. And where did I get that? I didn't pull it out of anywhere. I got it from the rules. That is on apparently table 4.1 on page, whatever page this one is inside of the book that I gave you to read, 156, inside of the chapter that I uploaded. Does that make sense to you? So really it's all about these rules that you read. Are we cool? The only last thing that we didn't do at this point is we didn't balance this equation. We need to balance this. So there should be a number out in front here, number out in front here, number and number in front of these elements, or in front of these compounds, so that way we can have the same amount of stuff on one side as the other. Now, I have 3 NO3s over here. How many NO3s am I going to have over here? Well, there's only 1 NO3 over here, so I'm going to have to put a 3 out in front. That 3 bumps that NO3 up.
Yeah, I can't really see this.
Okay. There. All right, here, let me just make it bigger than that. Like that.
There we
There. This 3 coefficient multiplies that NO3, so there's 3 of them. So now my nitrates are balanced. Do you guys agree?
Yes.
But the problem is my hydroxides are not balanced, nor are my potassiums not balanced. I've got 3 potassiums on that side. I've got 3 hydroxides on that side. And I've only got 1 on the left side. So maybe what's a natural choice?
The one on the left side, right?
Well, if I put a 3 in front of the one on the left side, now I have 3 potassiums. Now I have 3 hydroxides. I've got the same amount on my right side. I've got the same potassiums on my right side. And I have the same nitrates on both sides. So we're good. You guys see how I balance this equation? Kind of just go back and forth and give each side numbers until they match. Are we cool?
Yeah, I remember from physical science, so we did this, and some of them got to be like so ridiculously hard.
Yeah. It's not. They're not fun. I mean, well, it's not they're not fun. In fact, I even go through with you and I mean when I showed you guys that fraction trick, that's a really solid math trick that you guys can use. That was back in first quarter when we were balancing equations. All right, let's try this one. I've got potassium chromate, and I'm going to add it to barium nitrate. And that's going to yield me barium chromate, BaCrO4. And it's also going to yield me KNO3. Now, all of these are aqueous solutions except this barium chromate, which comes out to be a solid. Let's see. Do I have a picture of it?
How do you know it comes to be? Is it just in that little table?
Oh, by the way, this is what the previous problem did. It was this with the iron hydroxide. This is actually the iron hydroxide solid. We know iron hydroxide as what happens when you put iron and oxygen together.
It's the iron rust.
What?
It's iron rust.
You get rust. That's why it looks like that.
Yeah.
It's rust.
I thought that was some kind of rhetorical question.
Well, it's not a rhetorical question. It makes perfect sense. All right.
Okay.
So we are doing this thing. I don't know how you get. Well, I guess the best thing to do is to, How do we know what goes where? All right. Well, let's try to do this problem from scratch. In fact, if it's from scratch, we cross out this part completely. We just say, what happens when we put potassium chromate with barium nitrate? Question. Got it? All right. Let's go through this whole thing. All right. And I'm going to teach you guys some new equations. All right. So the balance equation would be, all right, well, if this were an aqueous solution, which they told me it was, and this was also an aqueous solution, and I know that this is an aqueous solution because if I go back to my rules that I have right here, see, these rules are really important. You might want to print them out and put them up on your wall or something like that. I'm serious.
Keep my important stuff on my fridge.
All right. Well, put it up on your fridge. Look, the nitrate is going to break down into its ions because rule number 1 says most nitrates are soluble. Boom, broken down.
Okay.
The potassium chromate, well, it says over here, most salts containing an alkali metal, hence a potassium, will break down in a solid in the thing as well. So these ions will break apart. So this would be K plus is my normal potassium. My CrO4 is a single minus. And how many Ks do I have?
2.
I've got 2 of those. How many CR4s do I have? Just 1. I've got my barium and my NO3. If there are 2 NO3s that have a negative charge on it, what must that barium charge have had to have to begin with?
Is that a 3 next to the NO?
That would be an NO3, yes, but
3.
there's 2 of them. No, nitrate ions have just a -1 charge, so this guy would have to have a +2 charge to balance out with those 2, nitrate ions, those 2 single negative nitrate ions. Are we cool with that?
Okay.
All right. And then what I'm going to do is, I think maybe what would be good is, since I'm not very good at this table yet, or maybe you're not very good at this table, I'm going to try to see if I can make some weird combinations. Like, I'm wondering if barium, Well, let's see. I would need barium, CrO4, and I would need two of those guys, right? Barium chromate and potassium nitrate. Got it? And I think I would just need one of those guys each. We cool with that?
Yes.
All right. Then I go back to here, and I'm wondering is barium chromate a solution? Is it gonna break down into a soluble, or is it gonna stay as a solid? And I look at my rules and I see, well, actually, what I'm doing, Bradley, is I know that it freaks you out that I'm doing this, but I'm just trying to see if I create those things, how would the rules apply to them? Are we cool? So I'm looking for the rules, and I know that potassium nitrate would just kind of break down back into ions, all right? But the barium chromate, is there any rules that you see about barium mixed with CrO4? I see rule number 6, and that has a chromate in it. It says anything mixed with the sulfide, chromates, or carbonates and phosphates are only slightly soluble. So that means it's going to be more of a solid as opposed to an aqueous solution. Except when you combine those with rule number 2. But rule number 2 is talking about alkali metals, so lithium, sodium, potassium, cesium, and rubidium. And so it's not talking about barium. So this barium chromate will probably form a solid. So that is probably the direction that my reaction is going to take. Does that make sense to you now?
Yeah.
Okay. All right. Now let's write down our balanced equation. So we started off with K2CrO4 plus BaNO3 with a 2 on it, and that's going to give me BaCrO4 2 plus KNO3. Is my equation completely balanced, or do I need a coefficient in front of them? And Bradley, you still don't see why I put them together. I guess the thing is, in chemistry, when we mix two chemicals together and some kind of solid forms, we wonder, well, what the heck just happened? And
I've wondered that.
if I had a clear solution, I mix them together, and I've got some kind of like rocks that form on the bottom, I'm wondering what kind of reaction just happened. And I guess my answer to that would be, well, obviously it can't be the original clear solution because you started off with two clear solutions.
I have a rock.
So there must have been some exchange of ions or cations and anions, and that's a combination of those cations and anions caused this reaction, and that's what that solid is. So we're trying to identify the solid. So in this case, we identified this one as the solid.
We should do a lab like
Does that make sense to you? And yes, absolutely. In high school chemistry, you do labs like that. And I will see if I can get my hands on some of the chemicals that we can do so we can
there's a black
make
market something for chemistry.
the labs like that. I think that it would be good to see what kind of things make precipitation reactions. How does it not make sense? I'm trying to think of how do I more clearly explain this.
What do you ask in the first place, Bradley? So I may have the same question.
Are you guys stuck on the same? Like I feel like I'm past it, but are you guys still stuck here? I'm not trying to single you out, Bradley. I'm just saying.
It is really difficult.
I think that Bradley. I think that what we're doing
is
we're trying to say, well, if a reaction took place, this is the only other combinations it could have had.
So it's not just.
And according to the solubility rules, do those combinations make sense? According to this rules in table 4.1. So I guess I'm throwing it out there and saying, if there was something to take place, if the reaction were to take place, these are the different kind of elements that could have been formed based off of what went in to begin with. So that's why I'm mixing them. I guess I'm just trying it. I'm trying to see if it does mix in the first place. And there are cases where, everything is soluble in the end, and so no reaction was going to take place in the first, to begin with. Does that make sense? In fact, I covered one of these. All right. Why can't CO3 go with CrO4? Oh.
Yeah, is this just like...
Wait, are you talking about the NO3? Why can't the NO3 go with the CrO4? Oh, that's an easy answer.
Is that just... Are we just trial and error there? Or is
No. Why can't you're saying why can't I combine the
in the very
the
beginning.
chromate with the nitrate?
Yes.
Because those are two negatively charged ions.
Oh.
Negatively charged ions don't get together. You need opposites to attract. Does that make sense?
Oh. Well, then why couldn't you just do the 2K, combine the 2K and the CrO4 negative?
Because that's what we started off with in the beginning. The 2Ks and the CrO4.
Oh.
And obviously something happened in this reaction, so it couldn't have been, if I pour the solutions in and they combine to form more of this and more are just the same amount of that and same amount of that, nothing happened.
That makes much more sense.
Yes, so I only put things together with opposite reactions, and I feel like maybe the best thing for me to do would be to bring you guys in and actually have you guys do these reactions. I don't have the chemicals on me. I'd like to get them. The problem is we don't have the money to buy a chemical cabinet, so I can't store the chemicals here. I can actually get my hands on some of these chemicals. I just can't store them anywhere. So what am I going to do? You see what I mean? So maybe what I'll do is...
You just got to get them right before you come to school and don't store them anywhere.
Yeah.
Just get them.
We can get them and
do the lab
just get enough just to use up all of the stuff we would have in the stuff.
Just keep making things. It's like playing Doodle God.
Beautiful reactions precipitation. I'll send you the link because it's gonna be all glitchy and stuff like that when you watch it on YouTube. Let's take a minute and 23 seconds and watch some YouTube videos.
Okay.
All right, give me a second. I'm going to send you the link right now. And by the way, is Bradley the only one here, or is there other people here?
There's like 5 people here.
Okay.
We're really starting to slack on our attendance for these.
You guys slack all you... Well, don't slack all you want, but I'm just saying, you guys are going to burn yourselves.
This is true.
All right. Here we go, Brad. Give me a second. Let's watch some videos. I'll text you something.
You're gonna text me?
No, I'll
Do you have my number?
I'll YouTube it to you.
YouTube. Do I get to watch this now?
Wait. Yeah, take it from me. If you miss the class, you're done for. No, you guys can watch it while you're sitting right next to me. You can watch it on my computer.
Okay.
All right, so check this out. I'm just going to talk about this as we go, but I think this is a reaction in air. All right, so this is silver nitrate with sodium strontate, and it creates sodium. What is SO3? Oh, sulfate. So here's barium chloride. So like the thing is, we're mixing two of these things together, and all of a sudden it's creating this like smoke or stuff, and we're like, well, what's going on? Oh, this is in water. Actually, I know that this one's in water. This one's silver nitrate with potassium chromate, and it's creating silver chromate. So those two, the silver ion and the chromate ions are combining together to actually make that solid. So my answer to you, Bradley, is no. You don't assume that the reaction will always take place. Maybe you only assume the reaction takes place when you see a reaction taking place. And you have to understand where this came from. We didn't come up with a theory first, and then we came up with the, we didn't come up with a theory first and then make an observation. We came up with, we observed this thing and we said, boy, I wonder what's happening. You see what I mean? We came up with the observation and then we said, from that observation, we're like, man, something funky is going on. Yeah. Turn on your mic. And I apologize. We might go past 3:15. I want to try to get done with this, but we haven't gotten anywhere, actually.
You lied to me?
No, I'm doing the best I can. But I also don't want to steamroll you guys and just kind of go right across and, don't care about what your questions are or whatever. Turn on your mic. I can't hear you.
Can you hear me?
All right, I can hear you now.
Okay. So, basically, like, what I mean is, if there isn't a reaction, if you don't assume that there's always a reaction, then why do the elements have to change in the first place? And if you assume that there is a reaction, then you just pair them up with the opposite charges. But if there's because you just said that don't
Bradley,
assume
1 second. I feel like I might need some backup. Celeste, could I get your help real quick?
Yeah.
I feel like I've done actually a good job explaining. I've got a student here who's kind of hitting the wall on something, and he has a valid question, and I'm almost wondering how do I explain it? So maybe if another teacher hears it and maybe adds your 2 cents in there, you can see where maybe coming from a different perspective might help them.
Yeah.
So just to kind of show you where we're at, we're reacting potassium chromate with barium nitrate. Okay?
Yeah.
These are both aqueous solutions, so I know that they break down into potassium chromate and barium nitrate. I also know that based on the rules. See, this nitrate is soluble, so it breaks down, and also the potassium. The potassium breaks down from the chromate.
Yep.
Right? And then I say, well, I don't know if the reaction does take place, but if one were to take place, then it would be such that they would switch these different, this. I always forget this. Is this an anion and that's a cation? Yeah. This anion combines with that cation, and this cation combines with that anion instead.
Yeah.
And then you create these 2 things. But then we can go back to the rules and explain why this thing is actually favorable in terms of being created, because over here in rule number 6 it says that chromate is actually only slightly soluble except when it's combined with a alkali metal, which barium is not an alkali metal.
Yeah. So
that's why that reaction takes place. But Bradley, if you're still on the mic, why don't you explain your question?
All right. So basically, if you don't assume that there's always a reaction, then why do the elements have to change? What other element they combine with in the first place if there isn't a reaction? Is it because if they break down and they're soluble, or because the rules, if they're soluble and they break down, that they automatically can't combine with the element that they were previously with, and that they have to change?
I guess his question is, how do you know a reaction takes place in the first place? Is that what you're asking?
Basically, how do you know which element it goes with if you don't assume that there's always a reaction?
If you don't assume there's always a reaction. You don't. Well, you kind of do, because if this thing is reacting anyways, then the structure of the element is going to be more favorable to the product. So you just assume that the swap takes place if it does. But if you're taking a step back, and then you're trying to figure out if a reaction takes place, that has to deal with structure resonance. Yeah,
that actually has to do with a more complicated topic, and actually that has to do. I think I remember doing this. That has to do with some numbers that we would assign to those things. Remember when I made you guys do the 3D periodic table? There's another kind of 3D periodic table where you have these um, uh, the reactivity
Yeah.
of substance, and then you would like look up on a table which one has more.
A favorable
It
reaction.
has to do with which one actually has less entropy.
Yeah.
That needs to
I
take
guess-
place. Which
I guess my
are
main
words
question-
I haven't taught
My
you
main
yet.
problem is if that came up and it said combine, or like if these elements were dissolved in water,
Uh-huh.
what new elements or compounds would be created? I
Okay,
don't think I'd be able to answer that. Because I
here's
don't know
my
which
answer
combine
to that, and I love where you're going with this. I love your inquisitive attitude, so don't give up on that. But here's what my answer would be: if a reaction takes place, this is what would need to have happened. It would have need to switch those cations and anions. If a reaction didn't take place, then you would be pouring in this stuff, and it would yield that same stuff right back at you. The question is,
Okay, so you're
yeah, so you only have one of two options to choose from. A reaction takes place or it doesn't take place. And if it takes place, this is your answer. If it doesn't take place, this is your answer.
okay, and by judging what's on the table, you can tell whether a reaction takes place or not.
And it's looking at the products, looking at the right-hand side. If you have things that actually create a solid, I think, or then the reaction is more favorable. Is that true?
Oh, it depends. Yeah.
Okay, so like if it just became an aqueous solution again on the other side.
Yeah.
then the
Okay,
reaction
fine. Here's a
takes
good.
place,
Here's a good thing.
change.
Let me try a problem for you. What if we did KNO3 and barium chloride, BaCl2? Okay? All right. KNO3, K positive, NO3 minus. Barium has got to probably have a positive 2 on it, and the chloride, there's 2 of them, so there's going to be a negative 1 on that. Are we cool?
Yeah, that's good.
Matching up my anions and my cations, this would, if a reaction were to take place, it would be this. It would be K plus Cl, and it would be BaNO3, or BaNO3 2. Are we cool?
Yeah. So,
but-
but what if a reaction?
Let me finish.
Oh, okay. So
But according
Okay,
to
yeah.
our solubility rules, anything with a potassium in it will break back down into its ions,
yeah.
K plus and Cl minus. And anything with a nitrate, according to rule number 2, but according to rule number 1, anything with a nitrate ion will break down into its ions. Are we cool?
Yep.
So, right up, in this reaction, no reaction takes place because when you put these guys together, you have a ion soup, right? Like just like broken down ions in your solution. And after the reaction takes place, if these guys formed, they would both break down into their ions again. And so you'd end
Okay,
up with
so-
ion soup. So in that case, no reaction takes place. Because it's
okay,
aqueous in
so-
the beginning, it's aqueous in the end, and aqueous means that those elements in water don't like if I basically what I would do is I wouldn't put pure potassium nitrate. I would have a solution of potassium nitrate. So I would take pure potassium nitrate and put it in water. Once I put it in water, aqueous means it breaks down. A soluble solution means it breaks down into its ions. You have potassium ions in that water, you have nitrate ions in that water. Same thing with the barium chloride. So I have water with potassium and nitrate ions. I have water with barium and chlorine ions. And I combine them, and I'm going to get more water with potassium, chlorine, barium, and nitrate ions, but nothing happened. Because the guys that tried to get together won't stick together, according to these rules.
Okay. All right. Yeah, that makes sense.
Was I right?
Pretty much. Yeah.
Whereas for this one,
Well, I mean, I get.
we know
okay,
that this
so
guy sticks
those are
together because
aqueous
he's a
solutions,
solid.
So,
Because he doesn't. He's not a soluble solution.
Yeah, but KNO3 would break down.
Yes,
back
it would break
into-
down. In fact, I'm going to get there when I start teaching you guys about complete ionic equation and net ionic equation and spectator ions and all that kind of stuff. Oh, yes. Tejas, there is something missing in this thing. This equation is not balanced. I didn't finish balancing the equation, but we got into a whole discussion. Celeste, thank you for your help.
Ooh.
Master, I need you as my wingman. Does that make sense now?
What?
You guys didn't even care.
No, I was outside. I didn't really hear the conversation.
Well, watch the video because we actually went into a pretty
I
awesome.
was planning on it.
All right, whatever. Okay. We didn't balance the equation. I need something in this equation. I think I need a 2 here. Do you guys agree? It's now balanced? Yeah, that's it.
Okay.
Oh, wait. Yeah,
Wait.
yeah, that's all I needed.
Wait.
I think
Yeah.
that's right. Yeah?
So
Everyone agree? Wait.
I already double checked. I think we're fine. Unless I missed something.
Oh. There should be barium chromate. Oh, I'm sorry. This barium has a positive 2 charge. Oh,
Yeah, the 2.
no, this barium has a positive 2 charge. But look, I accidentally put the wrong charge on the chromate. The chromate actually has a negative 2 charge. I can tell because I needed 2 potassiums to balance it out in the first place. So the barium chromate doesn't have a 2 over here. Sorry. My chromates got messed up. Now this is
That's what
correct.
the school gets for ordering Chrome.
Does this make sense now?
With the 2 gone, yeah.
All right,
I
good.
didn't even see the 2 in the first place.
Well, yeah, you got to be careful with that. So this right here is called a balanced formula equation. Balanced formula equation. Got it? Now, this is an aqueous. The only solid in this thing is the barium chromate. But everything else is an aqueous solution. So kind of going off what Bradley was saying, all of this stuff in the beginning, that wouldn't actually be potassium chromate because once you put it in water, this would be 2 potassiums, 2 K pluses, plus a CrO4 with a -2 because it took 2 K pluses to deal with it, plus Ba with a +2 and a 2 NO3s
Yes.
with a minus on that. And that would yield for me my barium chromate, BaCrO4. And I don't break that up into its ions because it doesn't break up into its ions. It's only, as the rules say, slightly soluble, which means not soluble.
Wait,
But-
really? What?
But what's
But it says slightly soluble.
well, slightly soluble is less soluble than actually soluble. In fact, I think they even have they have a blurb on it over here. It says, the phrase slightly soluble used in solubility rules means that the tiny amount of solid that dissolves is not noticeable. The solid appears to be insoluble to the naked eye. The terms insoluble and slightly soluble are often used interchangeably.
They're
just
so why
basic-
can't you just tell me it's not soluble?
Because it is soluble, it's just not enough soluble for you to be able to say it is.
Technically.
Well, we're jerks,
I
remember?
can't see it with my eye.
Well, that's exactly what they're saying. Anyway, as Bradley was saying, that this thing right here actually does break up into its solids or into its ions. Because, like you said, Bradley, this is still an aqueous solution. Or anything that has a nitrate in it is a soluble solution. And anything that has a potassium in it is a soluble solution. So KNO3 is doubly soluble. Does that make sense? All right.
Mm-hmm.
So this right here is called the complete ionic equation. It's the thing up above it. Got it?
So that's just
It's basically just showing you the equation, but all of the ions broken out as they actually are in the water. Okay?
okay.
Well, really, what happens is, see this potassium over here? I guess maybe one way you can kind of think of this is like, let's look at my complete ionic equation. Let me just write it down again. 2K plus CrO4 minus 2 plus Ba plus 2 plus 2NO3. I'm just rewriting what I had above. BaCrO4 plus 2K plus 2NO3. Well, really, with this reaction, this potassium right here is met up with that other potassium over there, right?
Yes.
And this NO3 can be canceled out with that NO3. So,
Well, that's 2 NO3.
well,
Oh,
there's
but
two
that's-
NO3s on the left side.
I thought that was something different.
So, really, my reaction happened between my chromium ion and my barium ion. And I don't need to... if I could make some kind of solution that only had chromium ions in it and only had barium ions in it, and I combined them, then it would make a solid of barium chromate, BaCrO4. And so these things that we have to begin with, the ones that we crossed out, those are called spectator ions. They didn't participate in the precipitation. They just kind of were watching, right? You could have taken them out and everything would be the same.
So why are they there in the first place?
The homework on tomorrow is not on any of this. Well, I'll tell you what. Bradley, after I'm done with today's class, I'll go through and I'll check all of the homework and adjust the homework according to where we're at. Okay?
Wait. See? Oh, I totally thought today was the 22nd. Oh, thank God.
Today's the 21st.
Yeah. So yeah.
All right. Anyway,
I got it.
so this right here is called the net ionic equation. So you have three different kinds of equations. You have got the balance formula, right? You've got the complete ionic equation, which is written out in its entirety, and then you have the net ionic equation, which is basically, I think of it as like the main players of this reaction.
Which one is the one that we should be using, or the one that we?
A lot of
The
times,
one that is most politically correct among the chemists of.
a lot of times, the chemist will use the net ionic equation
Because it's shorter. I'm saying?
because it just tells just the information that you need.
Okay.
But a lot of times people will use the net ionic equation, but it doesn't necessarily mean that it's always the best equation to use because you miss out on like, well, what kind of things do I need to combine? You know what I mean?
I think so. I feel like I know what you mean, but then I know that when I get writing this on paper, I'm not going to know what you meant at all.
Well, I'll tell you what. Let's just finish off chapter 4.6, and then on Monday I'll cover chapter 4.7,
Okay.
and I'll cover 4.7 and 4.8. We'll get to acid-base titrations and reactions. And then next week, Wednesday, I'll cover 4.9 and 4.10. And that will finish off chapter 4. So we're going to spend another week on chapter 4. Sound good?
Yes. Can we do like a lab or something?
Next week?
Where we can all come in and like practice all this together.
Yeah. All right, then we'll spend a week and a half on chapter 4. Because if we do a lab, what always ends up happening is if we do a lab, what ends up happening is we will that burns a whole day of time that I can do
Yeah.
things.
What are you doing for? Gridfest wouldn't working.
Yeah, no, Griffiths will be doing a lot of crazy stuff. Yeah, we'll do a lab next week Wednesday. We'll do a lab, and I will do my best to try to get you a precipitation reaction so you guys can see this, and also a titration reaction.
Just stay after Gridfest, Bradley.
Bradley, are you coming for Gridfest?
Type faster.
No, never mind. If you're asking what it is, you're not coming.
Darn it, dude.
Gridfest is on Friday.
They would have paid for you to come here.
Yeah.
I think that it had to.
And you had to buy a ticket, and then they would have paid for your ticket.
buy a ticket.
I don't know. You can call and ask if you can still come.
I mean, planes fly from Big Island here like all the time, though.
Yeah, I don't know.
If you buy a ticket,
The Gridfest is an opportunity for you to actually meet the Oahu students because thus far no one has actually met you.
this is true. However, you sound like a cool guy, if I may say so myself.
Yeah. People like you, they just haven't met you. All right, let's try a few more of these. All right. I've got potassium chloride added to aqueous silver nitrate to form silver chloride precipitate plus an aqueous potassium nitrate. Whoa.
What?
All right. Potassium chloride, I know how to deal with that. KCl. Potassium and chlorine. Good. And they said an aqueous silver nitrate. Silver is AgNO3.
What was that word before? What?
What?
Ag.
That's silver nitrate.
That's silver nitrate. But before that, there was some other A.
Potassium chloride.
And that, okay, never mind. Forget about it.
Here, I'll read for you what I'm reading straight from. Aqueous potassium chloride is added to aqueous silver nitrate. Aqueous
Okay,
basically
okay,
means,
okay.
well, I mean, you can look at the rules, and I don't want to go by what they're telling me. I want to go by what the rules are saying. You look at the rules. Look, potassium chloride, anything with potassium will break down. Anything with a potassium is an aqueous solution.
Okay.
Anything with nitrate is an aqueous solution. Got it? So actually, you know what? I'm only going to take half of what they say, and let's see if we can get the whole equation. Let's just go through this real quick. And I'm basically redoing what I just did for you guys, like for the last half hour, and then I'll redo it again. But I'm doing it quick. I'm going to do this one more quickly. All right. So, potassium chloride, silver nitrate. I know that these are both aqueous solutions because they follow the rules. They would actually form potassium ion and chlorine ion and silver ion and nitrate ion. Now, if a reaction were to take place, then this potassium would go with that nitrate and this chlorine would go with that silver.
Yes.
Okay?
And I now know why.
So let's see what would happen if I formed a potassium nitrate. Actually, I just need one potassium and one nitrate. And I would also just need one silver chlorate. Now, potassium nitrate, we know that will still break down into its aqueous solution, even if that's what's formed in the end. Got
It
it?
has potassium.
Because it has both potassium and nitrate. Rule 1 is nitrates. Rule 2 is potassium. That's doubly broken
So
down.
okay.
That has no chance of surviving. But what about silver chlorate? Do you see any rules about silver chlorate? Let me just take a look. Most chloride, bromide, and iodide solutions are soluble. That's not a good sign because that chloride is that. Noticeable exceptions are salts containing silver, lead, and mercury. Hey, that means that this thing forms a solid. So it doesn't break back down into its ions. So that's the reaction that's going to take place. KCl plus AgNO3 equals KNO3 plus AgCl solid.
I feel like whoever wrote these rules needs to be a little bit more specific.
And if I didn't write a solid there, then assume that it's aqueous. Right?
Okay.
And then, I mean, essentially, that's exactly the problem they gave us. Aqueous potassium chloride is added to aqueous silver nitrate to form silver chloride, AgCl, plus aqueous potassium nitrate, KNO3. All right? Well, that's the formula equation. Here's the full equation. What is the complete ionic equation? That would just be breaking all of the ions down into, well, what they'll end up breaking into. Okay, plus NO3 minus plus AgCl. So why didn't I break down the AgCl? I broke the
Because-
potassium nitrate into a solution, but I didn't break the AgCl into a solution. Why not? Because it's a solid. Yeah, there we go. And as you said, potassium nitrate has no way of surviving in the product of the thing because, no way of sticking together because the potassium is, rule number 2 and the nitrate is rule number 1. All right. So really, the potassium and the nitrate are actually just spectators.
So they're not even gonna.
So,
Not gonna
so
matter.
your complete solution is actually is this, but your net ionic equation would be Cl minus plus Ag positive will yield AgCl,
Great Scott, I think I've got it.
and that's it. That's the ionic equation.
I made a Back to the Future reference on Back to the Future Day. And
On
you still
Back to
didn't
the
even
Future
get
Day.
it.
No, I congratulated everyone on Back to the Future
Are you-
Day for the whole day, and so I've basically been tired of
I
doing.
said
the Back to
Great
the Future.
Scott. I exclaimed.
Dude,
Great
that's pretty
Scott.
heavy. I got
that.
I was there.
Okay.
I redeemed myself. How's that?
And Nike's actually making shoes that will tie themselves now.
Really?
Yep.
I wanted the jacket that dries itself off.
That's
And of course,
Yes.
everyone wants the hoverboard.
who doesn't want a hoverboard?
Yeah.
I mean, yeah. And Lexus is. Nah, it's not really a hoverboard.
All right.
Like the $1 billion skate park with whatever the metal is running underneath.
Yeah.
it.
I feel like I know I told you that I would cover only this 4.6 and then we would stop at 4. I want to cover 4.7 because 4.8 is a nice breaking point. It's where we cover acid-base reactions. So let's kind of cover this one. We're going to apply this idea. All right, I'll tell you what, Bradley. Here's what I'll do. I'll finish covering 4.7, much to your, dismay. You can leave now. It's up to you. I'll
Still
record.
unsure.
No, I'll record. And I'll record this. I'll put it up to YouTube. And then what I'll do is I will look at the homework and adjust the homework and pretend like I didn't cover 4.7 today. The only reason why I want to stick it with this lecture is because it goes nicely with this lecture. We've been covering precipitation reactions, so now we're doing the stoichiometry of precipitation reactions. No, you don't have to stay. I'll push the homework back enough for you to have time to watch the rest of it tomorrow on Monday. How's that?
We're pushing homework back now?
Yes, in chemistry I'm allowed to. In algebra I'm not allowed to. That's pretty cool. All right, let's see. Basically, we can use these things to apply to our stoichiometry things. So let's try this one. Find the mass of NaCl that must be added to 1.5 that add to 1.5 liters of solution of 0.100 moles of AgCl, or no, AgNO3. The solution to precipitate all of the Ag ions that form in the AgCl. Okay, all right, fine. So I'm not going to go through this, but essentially, well, okay, fine, I'll do it. Find the mass of Ag. All right, here we go. So sodium chloride breaks down. Why? Let's look at our rules. According to which rule does sodium chloride break down? Come on, we're going to do this one quick. According to rule number 2, perfect. So Na plus Cl minus. Are we good? And according to which rule does AgNO3 or silver nitrate do?
That's one.
That's rule 1. So that would be Ag plus and NO3 minus.
And I feel like I'm pro at this, but then I'm going to get the rules 4, 5, and 6. And it's just
No. I mean, they're just rules. You just look them up. Hey, your other. Most chemistry teachers would have you memorize this, and I'm not going to have you memorize this at all. Just look it up on the table. All right. It's going to form a compound, and I'm going to bet that compound is AgCl and also NaNO3. If a reaction does take place, right? And then we look at the rules and we say, oh, the NaNO3 doesn't have any chance of surviving according to rule 1 and 2. So that would be an Na plus and an NO3 minus. Those would break down to its ions. But the AgCl, I mean, according to the last conversation we had, remember, according to rule number 3, chlorides are soluble except for silver chloride.
So that says noticeable exceptions.
Noticeable exceptions.
Noticeable exceptions.
All right. So this is the reaction that would take place. I actually literally just wrote down the entire, the complete ionic equation, right?
Okay.
We did it together. So the NAs get killed. The NAs get killed. The NO3s get killed. The NO3s get killed. Those were just spectators.
So CLAG.
And then really you had Cl minus plus Ag plus gives you AgCl, which looks very familiar to me. And if you look right above, I have the same net ionic equation, even though I started off with different chemicals. I started off with potassium nitrate and I started off with potassium chloride and silver nitrate. And what I ended up, and over here I started off with sodium chloride and silver nitrate, and I ended up getting the same net ionic equation. It's because the main players are still the same in those ones.
Okay.
Does that make sense?
Yes.
So if I wanted to have solid silver chloride, then what I would do is I would either take sodium chloride, salt, and mix it with silver nitrate, or I would take potassium chloride and mix it with silver nitrate, and then I would end up getting some kind of a reaction, a solid, and then I would evaporate that thing so that way all of the ions and the water gets out of there, and I would be left with that powder that's left over, and that would be pure silver chloride. Cool?
Cool.
All right. Anyway, what this is saying is it's saying, now this is an equation. So equations deal with moles. So this is saying, and you know what? I'll tell you what. We'll go with your, if this were a blue Lego.
Oh, God.
And this were an orange Lego. Then I could create one blue and orange structure. How's that? So this is saying 1 mole of chlorine plus 1 mole of silver will give me 1 mole of silver chloride.
Beautiful.
1 mole of chlorine ions plus 1 mole of silver ions will give me 1 mole of silver chloride. And I know that you're not really down with that because your analogy was different to begin with. You wanted to combine this blue one and a yellow one to make a green one or something like that. And I feel like, yeah, I know. The blue and the yellow makes a green one, but I feel like that's actually a little bit wrong.
Blue and yellow makes green.
No, blue and yellow does make green, but when you mix the Legos, it doesn't. And you can't actually mix these things. You don't make a new... What that's implying to me is if I mix chlorine ions and silver ions, I'm going to make a totally different substance. No, what I would have is I would have silver chloride.
That's...
I'd have a blue-orange concoction.
Let's say someone should
So,
call Lego and tell them.
sorry,
work
I
on
hate,
that.
to, I hate to change your analogy. It was inspired by that, but I changed it a little bit so it actually makes more sense according to the math. Okay, so we can use this fact to give us a conversion. So if I have, what did the problem say? It said I started off with 1.5 liters of what? NaCl. So 1.5 liters of no. I started off with I want to make 1.5 liters of AgNO3. Got it? I know that. Oh, and how many ion or what's the concentration? Well, I know that the concentration that they wanted was 0.100 AgNO3 for every 1 liter. Where did I get that? Well, I got that from the problem. It was 1.5 liters that we wanted to make of 0.1 molarity AgNO3. We cool? And then I have to ask myself, okay, this gives me my AgNO3, right? But how many, and this is actually going along the lines of your question, Andre, is how many ions of AgNO3, or how many AgNO3s give me 1 silver ion? The AgNO3, 1 AgNO3 gives me 1 Ag positive silver ion. Does that make sense?
Sorry, I'm looking at the black guy. Is that just a picture of a random black guy, or is that like
No, I'll tell you the story later.
some
All right.
kind of sacred importance?
It is. Okay, wait. Let me finish this problem. And then that 1 silver ion is actually how many silver ions react with the chlorine ions. So this 1 silver ion reacts with how many chlorine ions? 1 Ag reacts with 1 Cl minus. Does that make sense? I'm looking at this net ionic equation for that information.
Okay.
And how many, and we're dealing with moles here, how many moles of salt can be produced from 1 chlorine ion? 1 mole of chlorine ions. 1 mole of salt. Got it?
I think so.
So now that I have the moles of salt, I can convert that to grams. I'll tell you how. It's very easy. You just say 1 mole of NaCl is 58.44 grams of NaCl. Ask me, where did I get 58.44?
Where did you get 58.44?
That's the molar mass of NaCl. You look at the molar mass of sodium, you look at the molar mass of chlorine, you add them together, that's 58.44. Because the molar mass tells me how to convert my moles to grams, and the question was asking me how many grams of NaCl do I need in the first place. So look, it's my giant conversion factor. I took 1 liter of this, that cancels out with liters of that. This tells me how many moles I'm dealing with, and once I'm in moles, I can use my equations. So 1 mole of AgNO3 cancels out with 1 mole of AgNO3. This moles of Ag positive cancels out with that mole of Ag positive. This moles of chlorine cancels out with that moles of chlorine. This moles of NaCl cancels out with that moles of NaCl. So really, all I got to do is, in my calculator, multiply 1.5 times 0.10 times 58.44. Because luckily, according to the stoichiometry, everything else ended up being 1, 1, 1, 1, 1, 1, 1. So that's equal to 8.77 grams of NaCl.
This is what we did. This is what we did all this last night. Homework.
Oh, this was homework?
This was homework last night. It was.
All right. Then what I'm going to do is I'm
I
going to
actually
take...
had to break out the pen and pencil.
Well, this is good. That means you actually had to think. All right, what I'm going to do is I'm going to take last night's homework. I'm going to push it back to be due on Friday.
I like checked and then I
This
double
Friday?
checked.
Yeah.
And then I triple checked and I.
I
still
know it's
got
Grit
15
Fest, but I mean,
points.
technically this was due last night. And I apologize for not having gone over this before the homework was due. And I'll push all the other homework back so that way we have
in trouble with the ions.
a chance to lecture on this. This is actually what we covered with
Yes,
ions.
Bradley, it was insane. I completely agree with you.
So
Didn't get it.
I
like
apologize for the
Google
stress that I might have caused,
everything.
and I will push the homework back for you,
I
so that way
tried
you
out.
have another chance.
I try. Eventually, I was.
In fact, I don't even know if I'm going to put. No, I'm still going to keep the 5 chances because do you guys use all 5 chances? Is that the problem?
no.
Yeah.
I don't. I
No one ever
usually
uses
go
all
through-
the 5. Oh, you do? Do you need more? Do you need like 10 chances?
Never mind. I stand.
I think it's because some people do trial and error.
I don't mind giving you 10 chances. I just don't want to give you unlimited
just like,
chances.
okay, did I get this right? Can we check again? Did I get this right?
Because what I also want to do is I want the computer to show you the answers in the end. And if I give you unlimited chances, it would never show you the answer.
Wait, what?
After your 5 chances, it shows you the
Shows
answer.
you the- I usually only use like 2 chances. If I use in my second chance, because I'm pretty. I tend
Alright.
to think I'm.
Our
Careful.
class is done, by the way. You guys can leave. I know that Bradley's itching to get out of here.
Ellie, you should totally try to come to Great Fest. I don't want to meet you.
You got to call.
Just like fly.
You got to
over here.
call
It's like,
Miss
what,
Watanabe.
45 minutes flight or something. It's
Call the
fine.
front office. Ask Miss Watanabe.
Yeah, dude. Do you like check your Canvas inbox like ever? Because she sends like 7.
She sent me like 3.
Oh, like
today.
honestly.
All right. I'll see you guys later.